Hi everyone, welcome to the ninth week of our NPTEL course on classical mechanics. So, before I start, I would like to first mention that there was a glitch in the recording when the live session was happening, which is why I am re-recording this session for those who watch on YouTube. Okay, with that said, let's start with the recap. So we had seen the Lagrangian of a heavy symmetric top, which involved theta dot, phi dot, and psi dot, right? And after lots of algebra, we were able to reduce it to an effective potential, which is a function of u, where u is cosine of theta. So it means that we can write our evolution equation for theta, and that looks something like this: u dot square is some function of u, right? Where all these parameters are functions of mz, m3, and i's. Okay, so and remember, theta is the angle between the axis of your top and the vertical axis. Okay, so first thing we notice is if u dot is equal to 0, then theta dot is also 0, which means theta is constant. So in that case, the theta won't change, and the top will undergo this precession motion without any change in theta. But if u dot is not equal to 0, then theta will change, and it will go from theta 1, some range theta 1 to theta 2. And this motion of theta is called nutation, right? We can prove that there must be some theta 1 and theta 2 because at theta is equal to 0 and pi, the value of u dot square is negative. So allowed region is only when u dot square is positive, which is this region. Okay. Similarly, the motion along phi axis, that is your this axis, is called precision, right? And phi dot is given by this thing. So depending upon whether phi dot could be 0 or not, you can have various types of motion. One is straightforward, when phi dot is always positive or negative. When it becomes 0, it has this vertical component, okay, and then it becomes negative, and then keeps on going. And when phi dot becomes 0 just at one of these theta boundaries, it just becomes vertical at the boundary, and then again keeps on doing this motion. So when we say it's moving along this path, it means the tip of the top or the axis is moving along this path. Okay. Then we saw about sleeping top, which is when if you start with some omega 3 without any theta, that is in vertical direction, you spin it. There is a threshold rotational speed above which the top would be stable, and as it goes on, and if this rotational speed decreases and comes down below the threshold value, then the top becomes unstable and it will go down. Okay, so we saw in the top part, and then we discussed something about rotating frame. So we have one inertial frame, which is the frame in which Newton's laws hold. Okay, so F is equal to ma, that is valid only when the frame is inertial. And obviously rotational frame, that is a frame that is rotating with respect to some inertial axis, is not an inertial. So uh, variation in time in inertial axis is different than that in rotational frame, and the relation is d by dt. The operator in the inertial frame is that operator in rotational frame plus omega cross. So you can apply this on any vector. Okay, so you may as well apply it on the vector r itself, that is the uh, distance vector, right? So displacement vector. So at the end, you can get the formula for acceleration in inertial coordinate is related to different quantities in your rotating frame. One of the best examples of this is us. We live on Earth, which is a rotating frame, right? So if you very carefully measure the forces on the objects on the Earth, you will see that force is not equal to mass times acceleration, and that is because of the fact that Earth itself is not inertial. So the correction terms to this MA part is there are three types of correction. First is Coriolis, which is 2 times omega cross V. Then there is centrifugal force, which we all are familiar with, right? If you ever been to a giant wheel or anything that is rotating in one of those spheres, then you know what this means, right? And there is Euler force, sorry, which is when the rotational speed itself is changing. So there is omega dot. Okay, so that was basically all that was covered during the week. Now let us look at some questions. So one thing I should tell you is that the assignment questions were not from the topics of the week. So nevertheless, we will solve the questions from the assignment, and then I'll solve a couple of more problems, detailed problems, which are related to content of this week. Okay, so as usual, the questions are pretty simple. So first one is that how many independent elements a 4 cross 4 symmetric matrix is. Okay, so 4 cross 4 means you have 4 entries here and 4 columns. Okay, so it will look something like this. Alright, and in this the matrix is given to be symmetric one. So obviously this diagonal entries can be anything, and we can fix entries in one of the triangles, say upper triangles. So these all could be anything, but once you fix the upper triangle, the lower triangle is already fixed, right? Because this is equal to this is equal to this one, etc. Right? So the independent elements are only from the upper triangle um, plus the diagonal elements. So how many of them are? 4 plus 3 plus 2 plus 1, which is 10. Okay, so the answer is third one. You can think it's very easy to generalize it to n cross n. The second one is how many independent elements a 4 cross 4 anti-symmetric matrix is. Now the property of anti-symmetric matrix is that Aij is equal to minus Aji. So if you put I and j equal, let's say 2, then it means A22 is equal to minus A22, which simply means that A22 is equal to 0, right? And this is true for any index, which means diagonal elements are 0. Okay, so now instead of diagonal elements plus the upper triangle, only the upper triangle have some independent elements. So you have 3 here, 2 here, and 1 here. All these diagonal elements are 0. Yeah, and again, once these elements are fixed, these elements are also fixed. They are just negative of the upper triangle, which means the independent elements are 3 plus 2 plus 1, which is 6. Right? Basically, you got rid of these 4 diagonal entries. So the answer is 6. Okay, good. And the last one is the matrix is given. A rigid body undergoes a change in orientation that is given by a matrix. So this is a matrix of rotation which we learnt about in last week, right? So the question is, which of the following vectors gives the direction of axis about which the rotation will produce the same orientation? So what we are asked is that a matrix is operated on this vector, but the direction does not change. Maybe the magnitude does, but this is same as saying that V is eigenvector of A, right? And indeed, they have given the hint also, a vector that is along the direction of rotation axis. Such a vector would be an eigenvector of A. Suggestion is to use Mathematica to do this problem. So let me just quickly show how easy it is using Mathematica. So in the first line, as you can see, I've just given the value of matrix. So the curly bracket is how you give the list, and matrix is list of list. So I give the first row, then second row, then the third row. Okay, and then I just write eigenvectors of A, where A is our matrix, and it spits out immediately these three vectors. And as you can see, two of them are imaginary, which means our eigenvector along the which is the axis of rotation is the third one. Okay, and the third one is not rationalized, so you have to multiply and divide by this square root of 2 plus 2. Okay, and once you do that, you will realize that uh, same as the first one, first option. Okay, so using Mathematica. Okay, cool. So those were the questions from uh, official assignments from previous one, and then let's discuss a couple of problems from the rotation change. So the first problem is called free-fall deviation, and the problem is as follows: there is an object and it is dropped from some height h and it drops down. And where does it fall? Of course, our preliminary understanding, which we learned in 12th standard or even BSc, says that it will fall directly below the point of drop, right? But of course, that is not true because now we know that the rotation is also at play, and because of this rotation, there is going to be a Coriolis force, and that is going to actually deviate, make the path deviated by some amount d. Okay, of course, I have exaggerated. I mean, in actuality, d is lot less than h, so that we do not really see the difference so much. Okay. So our task is to calculate d, and the equation is, we know that acceleration is given by g, right? That is the force on the apple, and plus 2 omega cross v, right? So as we can see, let's just quickly see. Yeah, in the inertial frame, it's 2 omega cross v. Okay. So in rotational frame, it should be minus of that. G minus 2 omega cross, right? Because we are calculating acceleration in the frame of Earth. In inertial frame, it's just G. Okay. Now let's choose our coordinate axis. Okay. So let's say this is our Earth, and we are dropping somewhere here. So this is our latitude lambda, and this is height h, and we are dropping like this. So this is z axis. Let's say this is x axis, and y axis is coming out of the plane of the screen, right? something like this. So x-axis is north, y-axis is, what would it be? This is north, y would be west. Okay, good. And the vector g is along this direction, and vector omega, because earth is rotating about the north pole, right, vector omega would be something like this. Okay, now the thing is, um, assumption, it's not assumption, rather justification for what we are going to do. Mod of omega is, we know, 2 pi divided by 24 hours, right? So which is 2 pi is what, around 6, so 1 by 4, and 1 hour is 3.6 into 10 raised to 3, right, seconds. So the omega is order of 10 to the power minus 4 second, or per second, right, which is very very small, which means this term, the term 2 omega cross v is perturbative, small perturbative, right? So now with that assumption, we can write our base solution, that is a solution without any perturbation, as just v is equal to gt, right, plus some initial u, right? This is coming from a is equal to g, right? So let's call this v base solution, and then actual solution would be, because there is this perturbative term, it would be the base solution plus some perturbative Vp, where Vp is small magnitude compared with Vb, right? So the equation is dv by dt is equal to g minus 2 omega cross v, right? Now we put v is equal to vb plus vp, so vb plus vp is equal to g minus 2 omega cross, again vb plus vp, right? And we know that d by dt of vb is just g, right? So d by dt of vb is g plus d by dt of vp. So what we want to know is this vp, because this is already known. Once we know the velocity, we can calculate the displacement, and from which we can get the final deviation. Okay, so we are trying to calculate this vp. This is equal to g minus 2 omega cross vb. I can write vb as gt, okay, and minus 2 omega cross vp, okay. And clearly the gg get cancelled, cg, and now we can make another assumption that since vp is small and omega both are small, this is order of omega square, right? Vp itself is order of omega, because if omega is 0, then Vp, which is the perturbative term, is also going to 0. This is order of omega, and this is also order of omega, which means we can neglect this term. Okay, which means d by dt of Vp is very close to 2 omega cross c t. Okay, we can integrate this, so Vp becomes omega cross c t square. Okay, so that our final solution becomes V is equal to some initial u plus gt plus omega cross g t square. So as you can see, this was the base solution which was order of t, but because of this omega, now we have order of t square term. Okay, now we can again integrate this. Right? Integrate so that r becomes h plus ut plus half gt square plus omega cross g t cube over 3. Cool. And so you can immediately see this was without rotation, right? 11th standard, chapter 1, 3, 4, and this is due to rotation. Okay, so now we need to go to this coordinates. Okay, let me just paste this picture there, copy, paste. So what would be our u? That is 0. We are just dropping it freely. Uh, then g is given by minus g z cap. Omega has x component, this north component, and z component, right? So omega is omega times, okay, if this is lambda, then what would be the lambda? This would also be lambda, right? Is that correct? Yeah, if lambda becomes 0, this angle also becomes 0. So this is lambda, which means the x component is omega cos lambda x cap plus omega sin lambda z cap, right? Anything else we need? No. Okay. So which means omega cross c term, which is required here, is x, y, z, the determinant of, then omega is omega cos lambda 0 omega sin lambda, and then g is 0 0 minus c. Okay, so x component is 0, y component will have term which is g omega cos lambda, right? And z component will be also 0. So you can see this is omega, and omega cross c has some positive y component. Okay, so now we can write, and our r would be, initial r would be h, so r0 is h, so now which is some h times z cap, right? So now we can write r equation, this one, z component would be hz component is h, and then plus ut, again u is 0, so this term goes away, and plus actually minus half gt square, because this vector g is minus cz cap, and then due to rotation there is only y component. Okay, so this is equal to 0, which means because at time t, some end time, it hits the ground. So t is equal to 2h by g, right? Time of flight is square root of 2h by g, which we know. And now we can calculate the y component. So for y component, this first all terms are 0, and the last term is omega cross g, which is g omega cos lambda times t cubed by 3. Okay, so and this is equal to the deviation d. So the deviation would be given by g omega cos lambda times square root of 2h by g cube, and there is a factor of 3. Okay, so we got our answer. It is this much. Okay, this is the deviation due to Coriolis force. Force is in force due to rotation, not a real force. Okay, so that was the first question. Now the second question, which is also again very interesting according to me, is that of Foucault pendulum. And the problem statement is that suppose we have a very long pendulum and it's oscillating, right? Then what would happen to its plane? So generally speaking, when we didn't know about rotation, we know that it stays in the same plane, right? Because there is no force perpendicular to the plane, right? But now we know that there is a Coriolis force again, which can rotate this plane. So if this is at initial time, after some long time, this plane can change, and now the oscillation would be along this plane. Okay, and that is your Foucault pendulum. There are museums where you can find one. In India, there is one in the Kolkata Science City, and I'm sure there are many other places where you can see this. Okay. So this is t is equal to some later time, and what we want to calculate is this rate of rotation of the plane. Okay, this omega 0 or something. Okay, so the idea is that suppose we are just interested in the x direction. Let's say this is our x direction and this is our y direction. Then x double dot plus omega square x, which was earlier just 0, right? Because it's a simple harmonic motion. But now there is a term due to this rotation, and that is 2 omega cross v, right? So when you do it, it turns out to be uh, vy omega z. Okay, and this is something you can calculate very easily with a factor 2. Sorry, and y double dot plus omega square y would be minus 2 vx times omega z. Okay, omega being the rotation of Earth, rotational velocity of Earth. Okay, so um, so how do you go from two one to one variable equations to one single two variable equations? So one beautiful way is to uh, construct a complex number z. Let's not call it z because it's confusing. Let's call it r, which is x plus iy. So in the xy plane, wherever your particle is, right, this is your complex number r. Okay, and then if you can find that r is given by some r0 into e raised to I omega t, then we know that this omega is the rotational speed which we want to calculate. Okay, so what we are trying to hunt is this exponent. Okay, so let's call this 1 and 2 and add both of them. 1 plus I times 2, so that the first term becomes r double dot plus omega square r. Okay, and this term will be, so let me just check so that I don't make any plus minus mistake. Minus 2I omega z r dot. Okay, because r dot is vx plus v I vy. Okay, so now I can write r double dot plus 2y omega z r dot plus omega square r is equal to 0, and this is a second order ODE that we have solved in past and we all know how to do it. The trick is to write r as some r0 into e to the power I omega t, right? You, you can place absorb I in the omega as well, both give the same answer. Okay, so then your equation becomes r0 into minus omega square e raised to I omega t plus 2y omega z r dot would be r0 I omega times e to the power I omega t plus omega square r naught e to the power I omega t is equal to 0. Let's cancel out this exponentials, then we can cancel out this r0 as well. Okay, so now the equation becomes minus omega square minus 2I omega z omega plus omega square is equal to 0. Okay, so I made one conventional mistake. I called both the omega same. So this omega is the frequency of pendulum. Okay, so let me call it omega p, so that this is omega p, this is omega p, and this omega stays omega in the Alsace. Okay, so this one is omega p, omega p. So omega square, let's get rid of minus sign, plus 2I omega z omega minus omega p square is equal to 0. So we get omega 1 and 2 as plus or minus, sorry, minus, was there an I? No, this I wasn't there. So minus 2 omega z plus or minus square root of 4 omega z square plus 4 omega p square, everything divided by 2. So this becomes minus omega z plus or minus square root of omega z square plus omega p square. Okay, and another thing is that this is roughly equal to minus omega z plus or minus just omega p. The reason is that omega p, which is the frequency with which the pendulum swings, is much larger than this omega z, which is the rotational speed of Earth. Right? Earth rotates once in a day, while the pendulum does many rotations in a minute or an hour. Right? So now the solution becomes r is equal to some a times e to the power I omega 1t plus b times e to the power I omega 2t, where omega 1, 2 are this quantities. So a times exponential of minus I omega zt and exponential of plus I omega pt and plus b times exponential of minus I omega ct times e to the power minus I omega pt. Okay, so I can take this factor out. So e to the power minus I omega zt, and this becomes a e to the power plus I omega pt plus b times e to the power minus I omega pt, right? So if I call this r0, then I have simply r is equal to r0 e to the power minus I omega zt, and this is what we were trying to hunt, right? So this is so the rotation speed of the plane of pendulum is just omega z, and we know from the previous one, right? Omega z was, where is it? Omega z is omega sine lambda. So this is omega sine lambda. So that's your answer basically. And then to make sense of it, let's calculate the time period. This is 2 pi divided by omega z. So omega into sine lambda, right? And 2 pi by omega, we know that's the time period of Earth, which is 24 hours. So this is 24 hours upon sine lambda, right? So in India, let's say near that line of 23.5 degree latitude, it passes through around, I don't know, Bhopal. You can calculate, you can check on Google the latitude of Bhopal, and it's roughly sine lambda is roughly around 0.28 or something. So the T is roughly 60 hours. Okay. So even I think in Kolkata it should be similar, around 60 to 70 hours. So if you look at the pendulum for 60 hours, you will see that it slowly completes one rotation. The plane of the pendulum itself completes one rotation. Okay, so that is your Foucault pendulum. This has some philosophical consequences as well. On one hand, it would appear that this indeed proves that Earth is actually rotating frame. It's not just that with respect to stars we are rotating, even without looking at the stars, looking at the sun in the dark room, we can find out the time period of Earth, which means it's an absolute quantity. But there is another school of thought as well, which says that how do you know that it's not the stars that is moving your pendulum? And in principle, we cannot resolve this, but clearly the first one seems more logical than the second one. So that is what all of us think, that indeed Earth is rotating. The rotation is indeed a some special thing, and an absolute thing. You don't really have to look outside. Okay, so with that, I would like to end this discussion. If you have any questions or queries, you can type it out in the chat box or in the YouTube comment box. And we'll see you next time in week 10. Bye bye. Happy learning.